Welcome back to Daniel's Extra Chemistry Help classes. In the last class, we discussed mole concept, conversion between mole, number of particles and mass of substance, role of Avogadro number, molar mass as conversion factors. Today, we will discuss percent composition of a compound, conversion of percent composition to empirical formula, conversion of empirical formula to molecular formula, and then problems based upon these concepts. Okay, the mole concept which we discussed is very important. We will be just coming to that again in the next some of the classes. So be careful to just be careful about that. Okay, let's go to the first thing in today's topic. Percentage composition of a compound. Okay, now this is basically almost the same as the mass ratio which we discussed when we are dealing with molecular formula. But when we have a new substance, we usually analyze it, and the analysis is usually done by using instruments. Instrument analysis usually gives percentages. So, the mass ratio of elements in a compound are expressed as percentages. So, that's the data, the standard data you are getting when we analyze a compound. So, when the percentage composition is given, you must know what it is. So, that's why we have here mass percent of an element in a compound is mass of an element divided by molar mass of the compound, that's the total mass of all the atomic masses together, times 100 to make it a percent. Okay, now let's take a typical example. So, water has two elements, hydrogen and oxygen. Okay, so if you want to find the percent mass of hydrogen and oxygen in this compound, what do we know? We needed the molar mass of water first. So, what is the molar mass of water? Yes, so got two hydrogens, which is 2, one oxygen, which is 16, add them together, you get 18. So, out of 18, 2 is hydrogen and 16 is oxygen. So, basically, you are going to convert that ratios into what? Into percentages. For example, percentage of hydrogen, mass percentage of hydrogen will be equal to 2 over 18. That is the ratio times 100, which gives you 11.1%. So what about oxygen? The same thing. You have to have 16 over 18. Okay. So for the oxygen, it is 16 over 18 times 100, which gives you 88.8%. So if you just say all the percentages in a compound, we call it as the percent composition of the compound. And if all the percent compositions are added together, you should get what? 100. So that's the idea of the percentage, you know that. Okay, let's go. Look at a particular question from your textbook. Question asks you, calculate the mass percent of different elements in sodium sulphate. And we know the formula, the molecular formula of sodium sulphate is Na2SO4, contains sodium, sulfur and oxygen. And for convenience, all the atomic masses are given here. If the atomic masses are not given, you will be using your periodic table and finding out the atomic masses. So, first what you have to find out? See, the percent of each element is the mass of that element, total mass of that element in the compound, divided by the molar mass times 100. So, first you have to find what? The molar mass. So, let's think about the molar mass of sodium sulphate. We got 2 sodium, so 2 times 23. 1 sulfur, so 1 times 32. 4 oxygen, so 4 times 16. And add them together, you get the molar mass, which is 142. Now, percentage of each element is what? The mass of that element in the compound, which basically is 2 times 23 for sodium, 1 times 32 for sulfur, 4 times 16 for oxygen. Divide that with the total, which is the molar mass times 100. Pretty easy, right? You can easily do that. So, sodium percent will be 46 over 142 times 100, which is 32.4%. Okay, sulfur will be what? 32 divided by 142 times 100, which is 22.5%. And finally, your oxygen is going to be 64 over 142 times 100, which gives you 45.1%. How will you check you are done correctly? Add them together. When you add them together, what should you get? You should get 100. Okay, there you go. Okay, so let's think about the empirical and molecular formula. What are they? Okay, molecular formula contains the actual number of atoms in a molecule. Okay, it actually shows how many atoms of each element are present in a molecule. While empirical formula is the simplest ratio of atoms of different elements in a compound. It only gives the ratio of atoms. Okay, now what's the relation between these two? Actually, molecular formula is the actual formula which gives you the real number of atoms. But always from an experimental data, we always go to the empirical formula. And the empirical formula is converted into the molecular formula. Let's take some examples for this to know what's the difference between these two. For example, if you take hydrogen peroxide, the molecular formula is H2O2 and the empirical formula is HOO. Where did you get that? We know the hydrogen oxygen atom ratio is 2:2, which on simplification become 1:1. So that's why the empirical formula is HO. Okay, so glucose, the molecular formula is C6H12O6. So by using the same idea, the atom number ratio is carbon, hydrogen, oxygen will be in 6:12:6, which simplifies into 1:1:2:1. That's why the empirical formula is CH2O. So I think you get the idea. So we can get the empirical formula from the molecular formula very easily. Okay, let's take a little example. Okay, so empirical formula can be obtained from the molecular formula by what? Taking any common factor in the molecular formula. So it's pretty easy if you want to go from the molecular formula to the empirical formula. For example, take the case C2H6, one compound. The carbon-hydrogen ratio, atom ratio is 2:6, which simplifies into what? 1:3. That means carbon 1, hydrogen 3. So the empirical formula will be what? Empirical formula is going to be CH3. So think about this. How will you find the empirical formula from the molecular formula of sulfuric acid, which is H2SO4? Okay, just try to find it out. Now, in all the problems we are calculating or trying to do, so if you're given a problem, stop there, just pause the video there and do the problem by yourself and try to get an answer. If you cannot go with the problem, what do? Just look at the strategy. I just give the strategy which gives you some clues. So after that, again try to do that. If you do this by your own, then you have a skill for doing problems. That's actually good. Okay, so in this case, what are the atom ratio for hydrogen, sulfur and oxygen? Is going to be 2:1:4, which cannot be reduced. Because the 1 is there, you cannot have any common factor. So here, the empirical formula is going to be the same as the molecular formula. So sometimes the empirical formula, molecular formula are the same. So in other words, you can say that the molecular formula may be the same as empirical formula or maybe a multiple of the empirical formula. This is the idea which you have to take from here. Okay, percentage composition to empirical formula. Let's do some problems based upon that. Percentage composition is what you get from experimental analysis of a compound. If it is given to you, that means the percentage mass percent of all elements will be given to you. Then how will you find the empirical formula? Okay, now atoms are so tiny, their mass is so small, we cannot actually deal with atoms usually. What do? We know that moles are more easier for us. Number of atoms and number of moles are proportional. We already studied in the mole concept. So the same thing which we defined as the empirical formula can be redefined like this. Empirical formula is also the ratio of moles of the elements in the compound. Now it will be easier if we just remember this idea. Instead of taking the atoms, in the case of experiment, you won't be given the atoms, you will be given the mass. So it's better to think of this. Empirical formula is the ratio of moles of elements in a compound. Keep that in your mind so that you can easily do the empirical formula from the percentage composition. Okay, let's take a typical example and do this. A hydrocarbon, that means a compound containing only hydrogen and carbon, on analysis is found to contain 80% carbon and 20% hydrogen. Find its empirical formula. A very simple question. So 80% carbon and 20% hydrogen. What does that mean? It means that if you take 100 grams of the compound, we have 80 grams of carbon and 20 grams of hydrogen. So that's the idea when you say 80% and 20% of the elements. Okay, now we can just what? Convert these mass of atoms into what? Moles of atoms. We already studied in mole concept. We can change the mass into mole by using, you remember that? The molar mass. And the molar mass of atoms are pretty easily got from what? From the periodic table. We have got the periodic table, and the periodic table gives you what? The molar mass of elements, which is the molar mass of atoms. So the molar mass of carbon and molar mass of hydrogen we can take from the periodic table. It is 12 grams per mole for hydrogen and 1 gram per mole for hydrogen. So we'll be using that to convert the masses of these elements into what? Moles. Now let's do it systematically. Let's put this in a table so that it will be easily, you can actually go from the one to the other. So let's think about this table. So on the first column we have elements, carbon and hydrogen. Second column we have the masses, which comes from the percentage. See, 80 grams and 20 grams. And then what? We are going to convert the mass into mole by dividing with the molar mass. So 80 over 12, which is the molar mass of carbon, gives 6.66. 20 over 1, that is 1 is the molar mass of hydrogen, that gives you 20. So since the moles are given, what is the empirical formula? Take the ratio. What is the ratio? 6.66 is to 20. But that doesn't make sense. We must have full numbers or integers or whole numbers as number of atoms. So what is the idea? So to make them whole numbers, you divide the factors inside in the ratio with the lowest or the least number. So select the least number, divide both the factors in the ratio with the same number. If you divide or multiply a ratio with the same number, the value of the ratio doesn't change. So you divide 6.66 divided by 66, which is 1. 20 divided by 6.66 gives you, around, it may be a 3.001. So whenever the number is going to be a 3.001 or a 2.99, which is very near to a whole number, always correct it. But never correct if when you divide, it is coming as a 1.5 or a 1.33 or a 2.25, just like that. If a 0.33, 0.5, 0.1, 25 comes, don't correct it. We can only correct when the number is very near to a whole number. Right? Just remember that. So once you get the 1 and 3 by the division, it is easy for us. Carbon is 1 and hydrogen is 3. So the empirical formula of the compound is just what? CH3. So pretty easy. Now, if you want to convert this empirical formula into molecular formula, what do you need? You need the molar mass. Okay, let's think about the next part of the problem. For the compound with empirical formula CH3, that is a continuation of the same problem, the molar mass is 30 grams per mole. Okay, find its molecular formula. Okay, we already know that molecular formula is the same or a multiple of the empirical formula. So, how will you find out what is the multiple? See, the n is the multiple. If n equal to 1, the molecular formula, empirical formula are the same. And if it is a higher number like 2, 3, etc., it is a multiple, of that empirical formula. How will you find the n? N is equal to molar mass, which is the data given to you, divided by empirical formula mass. Now, what is empirical formula mass? You add up all the atomic masses in the empirical formula, and that gives you the empirical formula mass. For example, this empirical formula is CH3. 1 carbon, 3 hydrogen. So, if you add up the carbon mass, which is 12, 3 hydrogen mass is 3, 12 plus 3 gives you 15. That's the empirical formula mass. And the molecular mass is already given, that is 30. So, what is the idea? You can find the multiplying factor n, which is equal to 30 over 15, which is equal to 2. Now what? You have to multiply throughout the empirical formula with this integer. So, CH3 times 2 gives you the molecular formula, which is C2H6. I think you get the idea. This is how we can change an empirical formula into a molecular formula. Okay. Now, a very interesting question from your textbook. It has a lot of ideas. So, let's just think about it, analyze this particular problem. So, as I already had told you, when you have a problem, just read it and try to do by yourself. And if you cannot do it or you cannot start that, look for the strategy. Some clues will be given in the strategy. So, let's look at the strategy. We are not given the masses of the elements in this problem. See, if you look at this problem, a welding fuel gas contains carbon and hydrogen only. Say hydrocarbon, okay. Burning a small sample in oxygen gives you 3.38 grams of carbon dioxide, 0.690 grams of water, and no other products. Okay, so the masses of the elements are not given. Carbon, instead of carbon, you are given carbon dioxide. Instead of hydrogen, you are given what? Water. And this is a usual way of analyzing a hydrocarbon or an element, a compound contains carbon. And then one more data is given, a volume of 10 liters of the gas measured at STP, standard temperature and pressure of this gas, is found to weigh 11.6 grams. Now that is a data to find the molar mass. So the molar mass is also not given. You have to find it out. So these are the things which are given. So it's basically a little, a problem which you have to think. So the first strategy is this. You have to find the masses of carbon and hydrogen using the mass ratio in the molecular formula of carbon dioxide and water. We know every compound has a particular mass ratio. For carbon dioxide, we got a carbon to compound ratio, hydrogen to oxygen ratio for water. Using that, you can find the masses of the carbon and the hydrogen from the compound masses. Second thing is, find the empirical formula from the mole ratio of elements, which you already seen. If you know the masses of the elements, so from the first thing you already said that you can find the mass of carbon and hydrogen, and then from the masses you find the moles, and then find the mole ratio, which gives you what? The empirical formula. Now, get the molar mass from the mass of the gas at STP. Now, we already studied that, you see, the Avogadro law gives you an idea about, it's actually an application of Avogadro's law. What is Avogadro's law? If you from the Avogadro's law, that application is, say, a 22.4 liters of any gas at STP contains 1 mole, and the mass of 1 mole is what? The molar mass. So that's the idea. So since the mass of 10 liters is given, we can easily calculate the mass of 22.4 liters. And that gives you what? The molar mass. And then once you get the molar mass and the empirical formula, what you can do? You can easily go to what? The molecular formula, just as we have done. So these are the data, or the strategy which we can use. Let's go one by one. Okay, let's go find out the masses of the elements, carbon and hydrogen. Now, if you look at the molar mass, or the molecular mass and the molar mass of carbon dioxide, we got 12 as carbon and 2 times 16 as oxygen. Add one together, we get 44. So in 44, if we take 44, out of that 12 is for carbon. So the ratio of carbon to the compound is 12 is to 44. That means 44 grams of carbon dioxide will contain 12 grams of carbon. So you can easily use that to find out what? How much carbon is present in the given carbon dioxide. So we use 12 over 44 times 3.38, and that gives you the mass of the carbon in the carbon dioxide. Similarly, we can also find the mass of hydrogen. Take water, H2O. In water, we have 2 for hydrogen, 16 for oxygen. Add them together, you get 18. That means what? Out of the 18, 2 is hydrogen. So if you take the ratio of the hydrogen, mass ratio of the hydrogen, this is 2 is to 18. So we use that ratio, multiply with the mass of water given, that gives you what? The mass of the hydrogen. Now, we have the mass of the carbon, mass of the hydrogen. So what is the next step? We go to the empirical formula by taking the moles. So we use a tabular column for that. So the tabular column goes like this. We got carbon and hydrogen. Masses are, we already found out. For the masses divided by the molar mass of each element. So 922 divided by 12 gives you 0.768. Then for hydrogen, 0.767 divided by 1, which is the molar mass of hydrogen, gives you the moles of hydrogen. So we have moles of carbon, moles of hydrogen. Then what? We have the ratio here, but they are not whole numbers. What we do? Take the smallest number, divide both of them with the smallest one. So here the smallest number is 0.767, divide both with that. And, approximately, basically you get a 1:1 ratio in there. So, if the carbon-hydrogen ratio is 1:1, the empirical formula surely is CH, C1H1. Usually we don't write the 1. So, that's your empirical formula. Now, what's the next step? You want to find what? The molar mass. Let's go to the molar mass idea. So, the application of Avogadro's law says what? The molar mass of any gaseous compound, or whatever the gas is the mass of 22.4 liters of the gas at its TP, coming out of the Avogadro's law. So, from the problem, it is given that 10 liters of the gas has a mass of 11.6 grams. You can use the dimension analysis if you want, because you can say that 11.6 grams to 10 liters are equivalent, and that is the what? That is the equality. I use that as a conversion factor. So 11.6 gram comes on the top, and 10.0 liter comes at the bottom. Multiply with the 22.4 so that the liters will cancel out, and that gives you the mass per mole. Mass per mole is the molar mass. So we get 25.98 grams per mole as the molar mass. So once we already have the empirical formula, we have the molar mass. What's the next step? Find the molecular formula. So what's the idea? We know the molecular formula is the same or a multiple of the empirical formula. So what we do? The multiplying factor n can be found by what? Molar mass divided by the empirical formula mass. We already done this in another problem, so we can easily do it. Find the empirical formula mass. Carbon 12, hydrogen 1, add them together, you get 13. So divide the molar mass with the empirical formula mass, that gives you a 2. So multiply what? Multiply the atoms inside the empirical formula with 2. So if you multiply, CH times 2 gives you C2H2, which happens to be acetylene gas. And acetylene is a very important gas industrially, because this is used for making oxyacetylene flame, having the highest temperature, which is used for welding and cutting of metals. So this actually shows the oxyacetylene gas. I think this was a very good problem. Okay, let's go to the next one. Determine the empirical formula of an oxide of iron, which has 69.9% iron, 30.1% dioxygen by mass. Now, all this is almost the same as the carbon hydrogen thing which you have already done. So this you can do by yourself. Try to do it. Okay, and then pause the video here, do it, and then come and check the how I have done it. So what is the idea? If you take 100 grams of the compound, mass of iron is 69.9 grams, And then mass of oxygen is what? 30.1 grams. Then what? Strategy is, empirical formula is the ratio of the moles of the elements. We already know that. Okay. Convert the masses of the elements into moles and take the simple whole number ratio. Okay, let's go look at that. In the tabular column, we have elements iron and oxygen. These are the, the masses 69.9 and 30.1. And then what? Divide with the molar mass. Now from the periodic table, you can get the molar mass of iron, molar mass of, oxygen. So 55.85 is the molar mass of iron. Just divide 69 with that, you get 1.25. 30.1 divided by 16 gives you 1.88. Now what? The ratio of these two will be 1.25 is to 1.188. And we already know that to convert them into whole number, we have to divide with what? The lowest number. So the lowest number is 1.25. So divide 1.25 divided by 1.25, 1.88 divided by the same number. You cannot change the number because we need to keep the value of the ratio. Now, it gives what? 1 is to 1.5. Now, don't correct it here. You can only correct if the number is very near to a whole number. So what is the idea? You have to, you can easily convert this into a whole number by multiplying with a lowest number which converts the 1.5 into a whole number. You easily know that. By multiplying with the 2, we can easily change the 1.5 into a whole number. So what is the idea? Multiply both terms in the, the ratio with the same number 2. So if you multiply by 2, you get this as 2, this is 3. So the ratio is going to be 2 is to 3. And so the empirical formula is going to be what? Fe2, because iron is 2 and oxygen is 3. So that gives you the empirical formula of the iron oxide. Okay, now this is another problem coming from your textbook. It's asked about how much copper can be obtained from 100 grams of copper sulphate. Okay, now this idea which you already discussed in the case of carbon dioxide, how to get the carbon from carbon dioxide and how to get the hydrogen from water. So basically, I think you know the idea. So what is the thing? You can just find the molar mass, okay? And the molar mass, how much copper is there? You can easily find out. So let's think about this. The strategy is this. The mass of the element can be found from the mass ratio in the molecular formula. So if you find the molar mass, 1 copper is 63.55, comes from the periodic table. So one sulfur is 32, and 4 oxygen is 4 times 60. Add them together, you get 159.55 as the molar mass. So out of that molar mass, your copper mass is 63.55. So you can use that ratio. So 159.55 grams of copper sulfate contains 63.55 grams of copper. You can take that as a ratio, or you can also do it as a what? Your dimensional analysis. If this much copper sulfate is equivalent to 63.55, then you can use a conversion factor where you can just have the 100 grams of copper sulfate, start with that. So the copper sulfate grams will come down and the mass of copper will be coming on the top for the conversion factor, and you can easily get the mass of copper from that. So what is the calculation? Mass of copper in 100 grams will be 63.55 divided by 159.55 times 100 gives you 39.8 grams of copper. So you can do this for any compound. You can find the elemental mass by using this idea. Okay, let's think about a very simple problem, This problem is pretty interesting. So try to think about it and you try to do by yourself. So without doing any calculations, determine which element in each of the compounds will have the highest mass percent composition. So you are given a compound, and from that you have to guess, or you have to find out without calculation which of the element has got the highest mass percent. For example, you take carbon monoxide. We got carbon and oxygen, and remember the percent is mass of the element divided by the molar mass. So in the total, how much is the contribution from each of the element? So if you take this case, carbon has contribution of 12, oxygen has a contribution of 16. So if you calculate the percentage, naturally the oxygen will have higher percentage. So that's the idea which you have to think about. Even you need not calculate, that will be the percent which is coming out. So you can say that oxygen is the element with the maximum or highest mass percent. So oxygen is the idea. So what about this case? N2O, dinitrogen monoxide. So here we got 2 nitrogens, which is 14 times 2, which is 28. 1 oxygen, which is 16. So basically, 28 is greater. So nitrogen is the element which has got the highest mass percent. Then we have glucose, which has got carbon, hydrogen and oxygen. So you have to take the mass of each element. So 6 carbons gives you 72. 12 times 6 is 72. Hydrogen 12 gives you 12. And 6 oxygens is 6 times 16, which is 96. And out of this, definitely 96 is higher. So oxygen is the element which has got the maximum or the highest mass percent. Finally, ammonia, nitrogen and hydrogen. Nitrogen is 14 and 3 hydrogen is 3. So definitely nitrogen is having the more or highest mass percent. So it's pretty simple. Sometimes you may be asked questions like that. So try to figure out or try to think about the percent, by looking at the elements. You need not calculate even. You can easily get it. So finally, we are coming to the last question, which is basically, something which you can, try to do. And if you're getting it, that will be a plus on your, so let's think about this one. Question is this. A metal M. Now, it's just an unknown metal, so we have to find it out. It's actually given as M. Forms a compound with the formula MCl3. If the compound contains 65.57% chlorine by mass, what is the identity of the metal? Okay, so this is the question. Think about it. So, you can actually stop at any stage and try to do your own. If you can do from this, that's okay. Okay, let's think about the strategy. We can identify the metal by using the atomic mass. So the periodic table, atomic mass of every element is given. So if you are able to find the atomic mass of the element, from the problem, you can easily identify the element. That's the thing. Okay, the given mass percentage of chlorine can be used to find the atomic mass. Remember, the mass percent calculation contains the atomic mass of each element. So naturally we can substitute that idea and you can easily find it out by an algebraic type of deduction. Just remember that. So we already know that percentage of an element is what? Mass percent of an element is mass of the element in the compound divided by the molar mass of the compound times 100. That's the mass percent of each element in the compound. So let's think about the problem now. So what is the data given? You're given the formula of the compound, the unknown metal 1 atom, chlorine 3 atoms. That's the molecular formula. Okay, and the percentage of chlorine is given 65.57%. And what is the question? You have to find the atomic mass of the element, and from the atomic mass you can figure out which element is that by using the periodic table. So let atomic mass of the metal be X. You're using algebraic idea. So the molar mass of the compound is what? Metal atomic mass is X, and then 3 chlorines is 3 times 35.45. Use the correct atomic mass of the chlorine given in the periodic table, because we have to be very, very careful here. So that's why we are using the correct atomic mass, 35.45 for chlorine. When you multiply that, that gives you 106.35. That is the molar mass of the compound. Now, percentage of chlorine by definition is mass of chlorine in the compound divided by molar mass times 100. Okay, mass of chlorine is what? 3 times 35.45, which happens to be 106.35. Divided by X plus 106.35, which is the molar mass, times 100 gives you what? The percent mass by mass percent of the chlorine. Now, that is actually given in the problem, which is 65.57. So now it's only just doing the algebraic part. You do what? You cross multiply the X plus 106.35 times 65.357, and that is going to give you the numerator. So so cross multiplying 65.57 times x 106.35 is going to give you what? 106.35 times 100. I just multiply that and the answer is written there. Now what? Divide both sides with 65.57. You get what? X plus 106.35 is 162.19 by dividing the right hand side with 65.57. Now what? Take away the 106, that means minus the 106.35 from both sides. That means you minus the 106.35 from right hand side and the value is got as 55.84. Once you get the X as that is the atomic mass of the metal. What? Look at the periodic table. Look at the periodic table. Find out the atomic mass which is nearer to 55.84. If you look at that, you can see that the element or the metal with 55.85 is iron, Fe. So that is the metal that is asked in the question. So it's pretty easy. It's an interesting type of question you have. So this is the whole thing which we have studied here. Thank you. And if you are interested, subscribe. Thank you. Bye.